Welcome back. We're now going to go through the work solutions to the nature of light worksheet 4A, special relativity, which focuses in on time dilation. This video will be for questions 1 through to 4. For subsequent questions, please see the next video. So the first question here is a craft is traveling at 0.4 c. That's 40% of the speed of light, and we need to state its velocity in meters per second. So we know that the speed of light, c, is equal to 3 by 10 to the 8th meters per second. So 0.4 c is 40% of the speed of light. So 0.4 c is just 0.4 times 3 by 10 to the 8th. And a very simple calculation, 3 exponent 8 multiplied 0.4, and that will be 1.2 by 10 to the 8th meters per second. Question 2, going backward, is asking us to work out what percentage of the speed of light is 2 by 10 to the 8th. So it's a very simple percentage question. So 2 by 10 to the 8th divided by 3 by 10 to the 8th, that's the velocity divided by the speed of light, multiplied by 100 would give us the percentage. The exponents by 10 to the 8th go in each case, so it's 2/3 as a percentage, so that's going to be 66.6% of the speed of light, or 66, maybe 60, just go 67%. Or if we were using it as a decimal, it's 0.67 c. The next is a table calculating gamma factors, the Lorentzian factor. So we are going to have to fill out the last 2 columns here, and just basically we're filling out each of these here. So I'm going to call this A, B, C, D, E, and F going down there so that we can keep track of our calculations. So looking at what we have to do for question 3A, we're given the percentage of light is 60%. That's a very simple calculation here. It's just simply the decimal version of that. We're going to work out its velocity and the gamma. So for 3A, the velocity is equal to 60% of the speed of light, which is 0.6 c. So the actual velocity would be 0.6 times 3 by 10 to the 8th. So that is going to be 0.6 times 3, and that will be 1.8. So it's 1.8 by 10 to the 8th meters per second. So the second column there should just simply have the 1.8 in it, because the by 10 to the 8th is in the top part of that column up here. The Lorentzian factor, the gamma factor here, is 1 over the square root of 1 minus v squared on c squared. Now, this is so much easier to use if we were to replace v squared on c squared as the decimal of light. So if we're saying in this case it's 0.6 c over c squared. Sorry, I'll just remove that square there for a few seconds, so it becomes much easier. So this is v on top, there is c on the bottom, and that's their squared. Rather than using this figure up here, which is 1.8 by 10 to the 8th, if we were just simply to use the decimal of light, the reason being is that c's will then cancel, and that gives us 0.6 squared. This means that the gamma factor is easy to calculate. When we use that, you get 1.0.6 squared. So this entire fraction is replaced by this decimal squared. Makes it much easier to calculate the gamma. Putting that into our calculator, 1 over the square root of 1 minus 0.6 squared. and we get decimal 1.25. Always check your gamma must be greater than 1, okay, because it's the ratio of the effect of relativity to the non-effect of relativity. In other words, in what happens in proper time. So if it equaled 1, there is no difference between the two frames of reference. Their times are the same. As this number here increases away from 1, and it will become infinite if V and if C becomes V, and so on. This becomes 1 minus 1. That means the ratio between proper time and time at motion becomes infinite. Right, moving on to 3b now. 3b in the table has a velocity of 2.4 by 10 to the 8th. So velocity is 2.4 by 10 to the 8th meters per second. Firstly, let's work out the percentage of C. So the percentage C would equal 2.4 over 3. Now the by 10 to the 8ths are on top and the bottom there, which would cancel. So I'm just using the first part of that number up here. Everything has been expressed with the same exponent. Calculating that as the fraction, 2.4 divided by 3 gives us 0.8. So this is 0.8C, so that's the decimal version of it, or 80% C. If we multiply that by 100, we'll get the percentage. Determining the gamma factor now, the gamma is 1 over the square root of 1 minus, and in this case, remember, we're not going to put in this number up here on C squared, we're going to use this here, and we're just going to use the decimal part, not that C. So it's 0.8, and don't forget that that has to be squared. So popping that into our calculator, it's 1 over the square root of 1 minus 0.8 squared, and it's 1.67. Okay, just always check your gamma factor is greater than 1. 3C is, we're given the first column, which is 75% of C. This becomes 0.75 C. The velocity would be 0.75 times 3 exponent 8. That's the velocity. And so that's 0.75 times 3. And that's 2.25 times 10 to the 8th meters per second. And the gamma at this stage is 1 minus, don't forget, it's just the 0.75. Don't forget to square it though. Okay, and putting that into our calculator, 1 over the square root of 1 minus 0.75 squared. And in this case, fantastic, it automatically came as a decimal, don't have to press that stupid button. 1.51. Okay, I am going to leave 3, D, E, and F up to you. I think there's not much challenge in it. Let us go to question 4. Question 4 is asking us for the first time to calculate time dilation. And the formula for time dilation is TV is equal to T0 on the square root of 1 minus V squared on C squared. That's the actual formula. But it's easier to recognize it as just TV is the gamma times T naught. It's so much easier. That means we can calculate the gamma separately, and then we just simply have to interpret the question as to whether we will multiply by that gamma factor or we'll divide by that gamma factor. So 4A, it says a spacecraft, look at it first. The spacecraft is traveling at 0.9% the speed of light and passes a stationary observer outside the craft. Okay. The first thing we're asked to do is calculate that gamma factor. The gamma factor will be 1 minus 0.95 squared. So that's 1 over the square root of 1 minus 0.95 squared, and that's 3.2. Okay, so that's the first thing we need to do. So we've now got that value there. Now remembering this number is always greater than 1. Since it's always greater than 1, this means the time at velocity will be bigger than the time at rest. And this is T naught is the stationary rest frame. And this is as you observe the object, the time happening in the moving reference frame. So part B, we have a look at the question. Part B says, how long does a stationary observer measure 15 seconds on the craft? Okay, so the stationary observer is looking at a clock, and their clock on the craft will see 15 seconds tick over, but because they're moving, that will take a longer time. So what will happen is the time measured on the clock, which is moving, which is TV, would equal 3.2 times the time measured that the observer would normally measure, which is 15 seconds. So multiplying that, that's 15 times 3.2, we get 48 seconds. So here is our moving reference frame, which has a clock in it. Okay, and the observer is seeing the clock tick around 15 seconds. So this is the external stationary observer. That's you standing on the side, and this one here is moving at 95% C. Okay, you are watching the second hand move from here to the quarter, the 15 seconds. You are measuring how long it is in your clock here as it ticks around. You will see 48 seconds of your clock pass before this gets down to 15 seconds. So that's what this number here is saying. You will observe 48 seconds on your watch when only 15 seconds of their clock has passed. Okay, for the continuation of this worksheet, please go to the next video.